Hello, today I'm going to introduce problem number 11 from IYPT 2020, Drifting Speckles. This is our observation video. As you can see in the video, as we are moving the camera back and forth horizontally, the laser spots and the speckles, which are these numerous little spots in the region of light, will both move accordingly, as the speckle seems to move faster than the laser spot. And then this is the problem statement of the drifting speckles. Shine a laser beam onto a dark surface. A granular pattern can be seen inside the spot. When the pattern is observed by the camera or the eye that is moving slowly, the pattern seems to drift relative to the surface. Explain the phenomenon and investigate how the drift depends on relevant parameters. So we think the main focus should be why speckles exist and why will it drift, and then how the speckles drifting will be affected by the characteristic of the observing camera. This is my outline. So first we have to know what is speckles. There are two kinds of speckles. As a coherent light shot at a rough surface, light reflected from such surface will set a contribution from many light-independent scattering areas. In this case, as the objective speckles, the propagation of these reflective lights to a distant observation position on the sensor will result in the addition of these various scattered light sources, which delays varies from several to many wavelengths, depending on the geometry of the rough surface. And the interference of these D-phase with coherent light will result in a granular pattern, which is known as speckles. And then in case of the subjective speckles, the light will first pass through a thin lens, then form images of the light source on the sensor at a proper imaging distance, just like lens imaging. The speckles on the imaging sensor are formed by the interference of related point source images and their neighbors. And as we determine the example of scattering light source and the lens as a diffraction hole, the smallest speckle size is set by diffraction limit. Larger angle lights produce smaller interference pattern and can be described as this, referencing the Rayleigh criterion. And as mentioned before, the smallest light spots observed on the image plane is limited by the aperture of an imaging system, which is called as the point spread function. Since subjective speckles are formed by the interference of these images' light source, larger point spread function can generally form larger speckles. Since delta dx is inversely proportional to the diameter of the lens, and that the smallest speckle size is equal to point spread function of imaging system, we can see that as the aperture becomes smaller, the minimum size of speckles will become larger and more visible. These information help us to choose smaller aperture in our experiments, since that can help improve the visibility of larger speckles. Then I'm going to discuss the movement of speckles and laser spots on the moving camera. So first we show a typical imaging with the camera. In this case, all the scattering point light sources are sharply focused on the sensor by the camera lens with the magnification M. As all scattering point source is imaged onto an imaging plane, the whole laser spots and all point sources within will be relayed on the sensor simultaneously. This means when the imaging camera moves transversely, all the image points, including speckles formed by the spreading point sources, and the whole spot will move at the same distance. Since there is no relative motion between speckle and spot, there will be no relative drifting observed. Then the first case happens then when the camera is focused on the image. You can see as the lens, which is the camera, is moving horizontally, the speckles as well as the laser spots will also move accordingly. In this case, the drifting speed of the laser spots and the speckles will be the same, can be described as this formula, which is as the moving speed of the laser multiple a ratio of the four lengths of the system divided by the distance between the sensor and the lens, which means when the camera is focusing on the image, the speckles will not drift relative to the laser spot. But in this case that the camera is defocused, the sensor is not at the imaging plane, the drifting will be different. There are two kinds of defocus. We can describe them using eye symptoms, which is myopia and hyperopia. Since the sensor isn't at the position of the imaging plane, we can determine it as related light source, which makes the interference pattern on the image plane become an objective speckle, which means that the optical path difference makes the speckles to drift along the surface and relative to laser spot. Then in this slide, we consider the speckle formed on the defocused camera, which means that the image plane of the illuminated object, which is a dark surface, is ahead of CCD sensor like myopia. To formulate the speckle movement, we first assume the speckle is formed by the complete constructive interference of two point source, which is the surface scattering of illuminating laser light. This means their optical path difference is zero as rest, which is the CCD original position. And if the camera then translates the distance delta s, the imaging of two point source will also be shifted the distance delta p as shown in this formula, which is the laser spot will also move delta p as in the focus mode. However, since the light from two different light sources incidents the lens of camera at an angle theta, and the optical path from such sources to image plane will from 2 points are different and can be described in this formula. In this case, the upper ray is shorter than lower ray. In order to form the same speckles with zero phase difference, the upper image point source now must travel longer distance than the lower one to compensate the path difference as illustrated here. After a few algebraic arrangements, the displacement of speckles and laser spots can be described with these two formulas, and their moving speed on the sensor will also be shown here, which indicates the magnification of the imaging camera M and sensor position away from the imaging plane, which is delta D, will affect the speckle drifting dramatically. And then in this slide, we consider the other case that speckles formed on the focus camera with the image plane of objects is behind the sensor, like hyperopia. The formulas then describe the speckles and the spot movements can be derived with a similar way as we did in the previous slide. The formula used in this case is just now having a negative sign like this. Then we will show our experimental setup. We use camera with a lens that can adjust the focal length to observe the motion of laser, light spots, and speckles on the rough surface, and use black paper or as required dark rough surface. By mounting the camera on a motorized translation stage, we can control the camera to move horizontally at a steady speed, which is 0.2 millimeters in our experiment. Then, these are the pictures shown our experimental setup. Then we will do our experimental results and discussion, and first with the experiment about aperture. We compare the photo of speckles taken with different diameter of the aperture. As can be seen, larger speckles within the spot are observed when the imaging aperture diameter diameter decrease as predicted by the theory. This makes easier to observe with smaller aperture, and the minimum size of speckles is inversely proportional with aperture size, just like point spread function. And as speckles become bigger, they are more likely to overlap and interfere, making the speckle size and the distance between speckles more large and more obvious. Then, by measuring the displacement of speckles with time for various diameter of aperture, which is 2, 3, and 4 millimeters, it is found that the speckles formed in all three cases move at the same speed. The drifting of speckles is completely independent from the size of aperture. However, in this displacement with time graph, you can see that I put 3 examples with different aperture. They fit each other quite well, while the formation of the speckles varies largely with size and pattern. Also, our experimental data agrees well with the theory that the drifting speed of speckles will not be affected by the diameter or aperture. Then, during the investigation on the working principle, we can see that the distance between sensor and imaging plane, which we define as delta D, will affect the drifting of the speckle strongly. So we set 3 cases, which are focus, myopia, and hyperopia, to assess the affection of the imaging sensor's position. First, in this case, the scattered light from the dark surface is imaged by the camera lens right on that sensor, which is delta D equals 0, and the lens is focused. Our experimental data shows that speckles and laser spots both drift at the same speed. Different focal length of camera lens gives different imaging magnification and change the drifting speed accordingly. The experimental observation will agree quite well with the theory prediction, as you can see in the slide. Then we change the focal distance and the focal position of the camera lens, making the imaging system perform like myopia situation. The delta D values is the distance that imaging plane is ahead of the sensor. We can see that the speckles all move faster than the laser spot, and that in comparison with our theoretical formula, our experimental results are fit quite well. On the other hand, if we set the camera to let the image plane behind the imaging sensor, like a hyperopia situation, the speckles are found to move at the opposite direction, while the laser spot is still moving at the same direction of the camera does. The relative motion between the laser spot and the speckles become obvious. In the hyperopia situation, the delta D is negative and causing backwards movement as predicted by the theoretical model. The displacement measures again shows our theoretical model can predict the drifting phenomenon quite well. Then, to further emphasize the effects of the image plane displacement, we keep all other parameters such as focal length, object distance, aperture size fixed, and move CCD sensor backwards. As predicted by our theory, larger the focus distance delta D results in larger drifting displacement difference between laser spots and speckles. The laser drifting speed of the laser spot speckles for different focus distance delta D can be summarized in this graph. Since objective distance L, imaging magnification M are constant numbers, the drifting speed of both speckles and laser spots are linearly proportional with delta D. And finally, a larger relative velocity between laser speckles and speckles can make the drifting more easily to be observed by bare eyes or image director. Instead of increasing delta D, smaller magnification M or object distance L, or ML, which is the image distance, can also help to increase the relative drifting velocity. Then moving on to conclusion. First, we found the aperture of diameter of the camera can affect the speckle size dramatically. When the aperture size increases, the average speckle size decreases as predicted by the theory, which is the point spread function. However, changing the aperture diameter only affects the speckle visibility, but does not vary the drifting velocity of speckle and spots. And secondly, by controlling the imaging plane ahead, right on or behind the sensor, the speckle and spots are found to perform different drifting behavior. If the image plane is right on the sensor, like typical camera imaging, the speckle and spot both drift at the same direction and same velocity. But when the image is focused before the sensor, like myopia, the speckles drift faster than the spot at the same direction as the camera moves. But, however, if the image plane is moved behind the surface, like hyperopia, the speckles and the spots drift at the opposite direction and drifting velocity. Finally, defocus the image away from camera sensor or eye's retina can make the relative drifting between speckles and spots become more visible. By simply increasing the defocus distance delta D, both individual drifting and relative drifting of speckle and spot will increase linearly with delta D. Thank you for listening.